All right, one more video for 7.5 where we learn how to solve trig equations. This video, it's a little bit misleading. I call it advanced equations, but I think what you'll find, the problems that we do in this video really aren't that much harder than the ones we do in the previous video. The hard part really comes at the end when you're trying to figure out the angle. But in this video, to get to that stage, you'll have to do a few more steps, things like factoring that you're probably okay with to begin with. But just in case you're not, I wanted to show you some examples. So this first one, for example, 2 cosine squared x plus cosine of x equals 1. If you're really good algebraically, you might have an idea how to solve that. If you look at that and have no idea how to solve it, think 2y squared plus y equals 1, right? Instead of cosine of x, change all your cosine of x's into y. You can even formally do that. Do a substitution, say let y equal cosine of x, solve it all, and then change your y's back to cosine of x at the end. Although I typically don't do that. I just kind of think about what would I do in this situation? Well, this kind of looks like a quadratic trinomial, and I sort of remember that the way I solve those is I set it equal to 0, and then I typically factor if I can. Other options are to use quadratic formula to complete the square. Factoring when the leading coefficient is not a 1 is a little bit annoying. There's a few different methods you can do. With numbers as small as this, you can kind of just do this guess and check method, where you're like, well, I need 2y squared, so I better throw a 2y here and a y here. And then the number that I put here and the number that I put here, when I multiply those together, they have to give me -1. So I'm going to need a +1 and a -1. But I have to be careful where I put them. Because, for example, if I put the +1 right here and the -1 right here, when I FOIL this back out, I wouldn't get a plus y. I wouldn't get +1 as the coefficient on this linear term. In order to make sure that if you FOILed this back out, you got back up to this stage, you're going to need the +1 to be on this side and the -1 to be on this side. The advantage of doing that factoring step is we now have something times something equals 0, and there's this thing called the multiplicative property of 0. You don't need to know the name. Essentially all it says is that something times something equals 0 is nice in math, because the only way that can happen is if one of those two somethings themselves equals 0. So I can go from this stage where I have one complicated equation to this stage where I have two more basic equations, the types of equations we solved in the previous video. But wait, this wasn't the problem that I was asked. I didn't ask anything about y's. I'm not supposed to do the problem in green. I'm supposed to do the problem in red. Right, but it's kind of the same thing. If you can look at this problem and think about this example, in this example, remember we saw something that kind of looked like a quadratic trinomial. So we first set it equal to 0, subtract 1 from both sides of the equation. And then we tried to factor this thing, and you're like, ooh, I don't feel comfortable factoring that thing in red. Green, maybe, but red, no way. Well, it's kind of the same thing. Just playing the role of the y is this cosine. In order to get 2 cosine squared x as my first term, I'm going to need 2 cosine x on one side and cosine x on the other side, just like I needed 2y and y over here. And then in order to get this -1, I'll need a +1 somewhere and a -1 somewhere, but I'll have to be careful where I put those, because if I put the -1 on this side, I won't capture this positive cosine of x if I were to FOIL this back out. The +1 will have to go on this side, and the -1 will go on this side. Again, thanks to my multiplicative property of 0, I got something times something equals 0. So that means either the first something, 2 cosine of x minus 1, is equal to 0, or the second something, the cosine of x plus 1 equals 0. You don't need any of the stuff in green if you can just do the stuff in red. But for a lot of people, it's hard to do the stuff in red. They don't realize that really they've already done this, just in a different context in a previous math class. At any rate, one way or another, if you can get to this step, what I now have are two what I would refer to as basic trig equations. 2 cosine of x minus 1 equals 0. That looks super familiar. I mean, it's almost exactly what we did as our first example in the previous video when we had 2 sine of x minus 1 equals 0. Similarly, cosine of x plus 1 equals 0 isn't that hard to solve. I solve these two equations, I get my solutions, and I'm done with this problem. For this first one, I want to get the x all by itself, so maybe I'll add 1 to both sides of the equation and get 2 cosine of x equals 1, and therefore cosine of x is equal to 1/2. Over here, it's just a one-step process. I subtract 1 from both sides of the equation, and I get cosine of x equals -1. Remember, these are not my answers. My answers are the values of x, and note that those x are limited to values between 0 and 2 pi. This is the stage where in the previous video we drew a picture. I'm going to do the same thing here. Here's my close enough to a circle unit circle. Cosine of x equals 1/2. Cosine is the x coordinate. The x coordinate equals 1/2 somewhere up here and somewhere down here. Cosine of x equals -1. The x coordinate is -1 right here. These 3 points will determine the angles x that are the solutions to this equation. Note that I want to make sure that I refer to them in the positive direction and keep my values between 0 and 2 pi. So I'll get pi over 3 for this value. And then for this value, I don't want to call it -pi over 3, even though -pi over 3 would take me here, because -pi over 3 is not between 0 and 2 pi. So instead of measuring it in the negative direction, I have to measure it in this positive direction. It's almost 2 pi, but not quite. I don't make it the final pi over 3. So it's 2 pi minus pi over 3. In other words, 5 pi over 3. This basic trig equation has these two solutions, but remember, this wasn't the question I was trying to solve. This was the question I was trying to solve. And solutions to this advanced trig equation can come from solutions to this basic trig equation or this basic trig equation. So I have two solutions, but there's going to be more based on this one. Cosine of x equals -1. Oh, right, that's this guy over here. Easy enough to refer to that as x equals pi. And you're like, right, but isn't it also 3 pi or negative pi or negative 3 pi? Yes, it is all of those, but our answers have to be between 0 and 2 pi. And the only angle that's between 0 and 2 pi that'll leave me at this point where the x coordinate equals -1 is an angle of pi. So this equation here has three solutions: pi over 3, 5 pi over 3, and pi. Often in the homework, they'll ask you to write them in increasing order. So you put this one in first, this one in second, and this one in third. But that's not anything I care about. If this is a test, you leave your answer like this, you're getting full credit. Let's do another one. 3 sine squared x plus 2 is what that's supposed to say. I left it off and I didn't want to erase. Sine of x equals 1. You stare at this thing and you're like, man, that's so similar to what I see in red here. I bet it'll be about the same difficulty as that problem was. Well, not really. The advanced, if you will, part of it will be the same as what we did in red. The part where we have to solve this like a quadratic will be almost identical to over here. All right, 3 sine squared x plus 2 sine of x equals 1. Maybe you're thinking something very similar to what you see in green, except it's 3y squared plus 2y that's equal to 1. But if you had that equation, much like this equation, you'd first set it equal to 0. So 3 sine squared x plus 2 sine of x minus 1 equals 0. And then you try to factor this thing. And factoring this thing won't be much more difficult than it was to factor the one that we had in red. We want our leading coefficient to be a 3 here. So I'll need 3 sine x in one of these parentheses and sine x in the other parenthesis. And then to get a -1, I'll need a +1 on one side and a -1 on the other side. But in order to recover this 2 sine of x, if I were to FOIL, the +1 will have to be on this side and the -1 will have to be on this side. Don't believe me, FOIL this out. Make sure you get back up there. Now I have something times something equals 0. The fancy name for what I'm doing is exploiting the multiplicative property of 0. But you don't need to know all that. All you need to know is solutions to this one equation come from any solutions to either of these two equations. Solving these guys isn't too bad. For the first one, add 1 to both sides of the equation, and then divide by 3, you get sine of x equals a third. Over here, just subtract 1 from both sides, you get sine of x equals -1. We're at a step similar to this step right here. We're done with the advanced part. We've isolated the trig functions. What we have to do now is think in terms of our unit circle. And maybe you're seeing where this is going. Cosine of x equals 1/2, that's not that bad, right? Those are points I have memorized on my unit circle. Sine of x equals 1/3, that's miserable. Those are not points that I have memorized off my unit circle. We're going to have to use inverse trig functions like we did in the previous video. Sine of x equals 1/3, that's the y coordinate. The y coordinate equals 1/3, I don't know, roughly here. So we're talking about some angle over here and some other angle over here. For the sake of color coordination, I'll make this one blue and this one green. If I want to get x all by itself, I can take the arc sine of both sides of the equation. If the sine of x equals 1/3, that means x is equal to the arc sine of 1/3. But be careful, you have to worry about the restrictions to arc sine. Arc sine is restricted to the right-hand side of my unit circle here. Arc sine is restricted from -pi/2 to +pi/2. So when I say arc sine of 1/3, it's not talking about both of these points. Either of these points have a sine of 1/3, but arc sine of 1/3 is only talking about this one. It's only talking about the one over on the right-hand side of my unit circle. It's always a number between -pi/2 and +pi/2. Fortunately, in this case, that number is a positive number, so I'm within these bounds from 0 to 2 pi. The arc sine of 1/3 refers to this angle right here, and it's one of my two solutions. What I now have to do is refer to this angle in green by exploiting the symmetry of a circle and using the fact that the angle in blue is the arc sine of 1/3, because the distance from here up to green is the same as the distance from here up to blue. So I can think about green by going halfway around the circle and then backing up by that amount, which I've referred to as the arc sine of 1/3. What I'm saying is another solution would be pi, halfway around the circle, minus this angle, which is arc sine of 1/3. Man, that's hard. Yeah, it was hard, but it was hard in the previous video as well. It's not harder because we're doing advanced equations. The only advanced part of it is being able to factor to get down to here. Just like I told you in the previous video, expect these more often than not to be values you have memorized off your unit circle. And you're like, all right, fine, moving on. No, be careful. We haven't solved this one. Sine of x equals -1. There is a point between 0 and 2 pi on our unit circle where the y coordinate equals -1. We're talking about down here. So how do I refer to that angle? Well, I got options. I could refer to it this way as -pi/2, or I could refer to it this way as +3 pi/2. But if you refer to it as negative pi over 2, you're coming up with a solution that's not in this restricted range. So you better refer to it as 3 pi over 2. That was a hard one. Let's do one that's a little bit easier that technically qualifies as an advanced equation. We're going to have the same restriction on our angles x, and we got sine squared x equals 1. For this one, since there's only a single x in the equation, unlike up here where I had x's in this term and x's in this term, it'll be a lot easier. I just have to isolate that x. To get this x all by itself, maybe I could first get sine of x all by itself. The way I can do that is take the square root of both sides of the equation. But be careful, when you take the square root of both sides of the equation, you got to put in this plus or minus, and that'll be important. The sine of x equals plus or minus the square root of 1. Well, the square root of 1 is just 1. So what I'm looking for are values of x so that the sine of those angles is either positive 1 or negative 1. Maybe it'll help to write this twice. Sine of x equals 1. Sine of x equals negative 1. You might immediately know what those angles are, but I'm going to draw the unit circle just in case. The sine is the y-coordinate. The y-coordinate equals 1 up here, and it equals negative 1 down here. Be careful. Make sure you measure them in the positive direction so that your angles are between 0 and 2 pi. So the solutions to this point, which come from this equation over here where the sine of x equals 1, is when x equals pi over 2. And the solutions to this, when sine of x equals negative 1, referring to this point, is 3 pi over 2. Note that it's significantly easier when you get values off your unit circle here, and you don't have to use this inverse trig stuff that we used in this blue example over here. That's all for 3. That's the answer. However, I want to show you a different way you can come to the exact same conclusion. And that might seem like pointless, something that math teachers like to do for no real reason. But I think what you'll see is that in this specific example, it's optional. But in the next example, it'll be something you'll want to know how to do. So let me redo 3. We started out with sine squared x equals 1. If I felt like it, and you might argue, why would you feel like it? But don't worry about that. If I felt like it, I could subtract sine squared x from both sides of the equation. That would change my equation into 0 equals 1 minus sine squared x. The reason why is because this might be a form that you recognize from the Pythagorean identity. Recall your Pythagorean identity is that for any angle x, sine squared of that angle plus cosine squared of that angle has to be equal to 1. So if I take this identity and I subtract sine squared from both sides, I get that cosine squared x is the same as 1 minus sine squared x. So if I'm ever lucky enough to see 1 minus sine squared x in the wild, I can change that into cosine squared x. Hey, here's one right here. I could rewrite this equation as 0 equals cosine squared x. To solve this equation for x, first let's solve it for cosine of x. Take the square root of both sides of the equation. Yeah, you should put in the plus or minus, but you really don't have to, because the square root of 0 is just 0 and plus or minus 0 are both just 0. What I'm saying are the solutions are angles x when the cosine of x equals 0. Well, the cosine is the x-coordinate on my unit circle. Looks like that happens, oh, right, down here and up here. I'm going to get the exact same answers that I got over here. All right. I mean, I guess that's kind of cool that you can get the same answers 2 different ways. I thought this way was a little bit easier because it didn't rely on me recognizing the Pythagorean identity. That's a fair objection to me doing this the way in green, but let me show you another example. All right, let's do another one, number 4. So we have the same restriction on our angle x. It's supposed to lie between 0 and 2 pi. And this time our equation that we're solving is cosine squared x minus 4 sine of x minus 4 equals 0. Like enough of these ones that kind of look like quadratic trinomials. I get the point. I factor this thing, thinking about it kind of like these are y's in this place, get to this point and solve these equations. This is just like 1 and 2 again. No, it's not. It's very different. The reason why is because it's cosine that's being squared over here, but it's sine that I have here. When those trig functions don't match up, you can't do that trick, because essentially what that trick was substitution. The y is playing the role of the cosines over here. We can't have y play the role of both cosine and sine within the same equation. Okay, so what do I do when I have cosine squareds and I have sines over here? Well, you got to change the cosine squareds into sine squareds. How you going to do that? Pythagorean identity. In fact, we just did that a minute ago, right? Remember, the Pythagorean identity told us that cosine squared x was equal to 1 minus sine squared x. Admittedly, when we use that in number 3, it was 1 minus sine squared x that we changed into cosine squared x. But equality works both ways. If I have 1 minus sine squared x and want to change into cosine squared x like I did here, great. If I have cosine squared x, I can change that into 1 minus sine squared x if for some reason I want to. And right now, I very much want to, because doing so gives me just a single trig function sine of x that appears in this equation, so now I'll be able to factor it like I did the previous ones. When you stare at this, it might not look like a quadratic trinomial because you have this 1 and this negative 4 here, but you can always combine like terms and make this negative sine squared x minus 4 sine of x minus 3 that's equal to 0. The negative 4 and the positive 1 net out to negative 3. And then you could factor this thing. And you could factor it just how it's written right now. But generally speaking, when the leading coefficient is not positive 1, it's a little bit harder to factor. It's doable. We did it up here. where the leading coefficient was a 2, and we did it again over here where the leading coefficient was a 3, but it's certainly easier when the leading coefficient is a 1. We could do it with the leading coefficient of -1, but trust me, it'll make your life easier if we could make this a positive 1. The way you can make this a positive 1, well, multiply both sides of the equation by -1, or if it's easier for you to see it this way, add all this stuff over to the right side of the equation, so you get 0 equals sine squared x plus 4 sine of x plus 3. Factoring this isn't too bad. I need two terms. Because my leading coefficient is a 1 here, I need sine squared x, so it'll be a sine x over here and a sine x over here. And now all I got to do is find two numbers to put here and here that when I multiply them give me positive 3, and when I add them give me positive 4. Let's see, positive 3 and positive 1 I believe will do the trick. So now I've factored this quadratic trinomial, and so I can apply my multiplicative property of 0 and say sine of x plus 3 equals 0, or sine of x plus 1 equals 0. Solving these equations, no problem. Sine of x equals -3 or sine of x equals -1. Now we go to our unit circle. The sine is the y-coordinate. When does the y-coordinate equal -1? That's down here. If I want to be between 0 and 2 pi, I'll refer to that angle as 3 pi over 2. When does the sine of x equal -3? It doesn't. Oh, I got to use like arc sine or something? No, there are no solutions to this equation. The sine of x cannot be equal to -3. On my unit circle, the y-coordinate will never be equal to -3. Because remember, here's 0, here's -1, -2. -3 is way down here. My unit circle has a radius of 1. It's never getting down to -3. There's no solutions to this equation. So the only solution to this equation comes from this one. It's this 3 pi over 2. One more example, then we'll call this video good. Same restrictions. We want our angle to be between 0 and 2 pi, and we're given this equation here. This looks like a mess, but I think you'll find this isn't as bad as it seems. This equation is already set equal to 0. That's good news. If I could factor this, I'd be in really good shape. I could apply that multiplicative property of 0. I can factor this because each of these terms has something in common, a tangent of x. I can pull tangent of x out of this term, and I'm left with just the square root of 3. And I can pull tangent of x out of this term, and I'm left with just 2 times the cosine of x. This might not seem like a big improvement from what we started out with, but it is because it's something times something equals 0, which is a great place to be in math. This is telling me that either the tangent of x equals 0 or the square root of 3 plus 2 times the cosine of x equals 0. These are both equations that I can solve. These would fit in the previous video where we're talking about basic equations. This one is basically done. This one, to get cosine of x all by itself, maybe I could subtract the square root of 3 from both sides, and then I could divide both sides of the equation by 2. I'm at the stage where I go to my picture. The tangent of x equals 0. Remember, the tangent is the y-coordinate over the x-coordinate. The way you're going to get that fraction y over x to be equal to 0 is if the top, the y value equals 0. The tangent of x equals 0 over here and again over here. How do I refer to those angles? Well, this one is just 0 and this one is just pi. And then you're like, wait, shouldn't you include 2 pi as well? No, because I want my angles to be greater than or equal to 0, but strictly less than 2 pi. So I would not include 2 pi over here. When does the cosine of x equal -√3 over 2? Well, the cosine of x is the x-coordinate on my unit circle, and the x-coordinate equals -√3 over 2 at the points that are kind of roughly speaking over here and over here. A distance of pi over 6 in the positive and negative direction from pi over here. If that helps, great. If not, just go back to the unit circle that you have memorized, and I think what you'll see is that at 5 pi over 6 and 7 pi over 6, you had written x-coordinates of -√3 over 2. This specific example has 4 solutions, 0 pi, 5 pi over 6, and 7 pi over 6. Note that all 4 of those values are between 0 and 2 pi, whereas if I referred to this last one as -5 pi over 6, it would not be in that range. The point of this example was more to remind you of techniques that you already had for solving equation. Just like you could factor a y out of the left-hand side of this equation, you can factor a tangent of x out of the left-hand side of this equation. Look for things that all terms have in common if your equation is already set equal to 0, and often that factoring will help you in solving.